let's quickly recap what we were discussing last time. So we discussed what a matching in a graph is. So a matching in a graph is a subset of edges such that no two edges in the subset have any endpoints in common. And we discussed certain types of matchings last time. There's something called a Maximo matching, which is a matching which cannot be enlarged any further. So you cannot add any edge to a maximal matching and still have a matching. We also discussed a maximum matching, which is a matching in the graph of largest possible size. And we saw that a perfect matching is a matching that touches every vertex. Okay, and the matching problem is basically the following. Given a graph chi as input, the problem is to find a maximum matching in the graph. So for example, for this particular graph right here, if that graph is your input, forget the fact that some of the edges are solid and some are shaded. That's just to illustrate to you whether the solid edges form a matching or not. So you have a graph here, and the number of edges here is 1, 2, 3, 4, 5. You have a bipartite graph here on 5 edges, and the goal is to find a maximum matching in this graph and then to output that maximum matching. So for example, the solid edges, that is a matching because the two solid edges have no endpoints in common. They do form an independent set of edges. However, this solid edges is a matching of size 2, and we want to output a matching of largest possible size. Now, what is the largest possible size of a matching in this graph? It turns out that you can actually have 3 edges that still form a matching. So here you can have A getting matched to Z, C getting matched to X, and B getting matched to Y. Okay. So that's a matching of size 3 in the graph. So the matching described by the solid edges is maximal, but not maximum. The reason it's maximal is because you can't add any other edges to the two solid edges and still get a matching. Basically, vertices A and X are matched and B and Y are matched in the solid edges. Only C and Z are not matched, but any edge you can possibly add is going to be, either touching X or touching A. Okay. If any edge which is touching C or Z is going to be touching A or X, but A and X are already matched. So the solid edges form a maximal matching, but not a maximum matching. And we kind of briefly looked at some offline algorithms for maximum matching. And there's a very famous algorithm by Edmonds and Karp for finding a maximum matching in a graph. And you can formulate these problems in terms of network flow problems. Okay. The thing here is that even though these algorithms for finding a maximum matching in a graph run in polynomial time, the problem is they require you to know the entire graph in advance, whereas what we need for the ad allocation problem is an online algorithm. So last time I briefly covered a particular greedy algorithm, but since my voice wasn't clear, as some of you pointed out in the discussion forum, probably I should go over it again. So what I'm going to do here, in fact, I watched the video myself and found the font size of some of these to be pretty small. But I hope now the font size is clear, and we're going to go over the greedy matching algorithm today. And in particular, we're going to actually see a proof of the worst case performance of the greedy algorithm being exactly 1/2. Okay, so we want to solve the maximum matching problem, but we're going to look at a greedy algorithm which solves this problem approximately.